This is the largest dam in the Colorado River Basin. It powered the growth of Las Vegas, Los Angeles, and Phoenix. And right now, in 2026, it's losing power fast. Hoover Dam's output is set to fall by 40% of its maximum capacity this year alone. And just upstream, a second dam is sitting only a few dozen feet above the threshold where it would stop generating power entirely. This is the story of America's most famous piece of infrastructure, and the slow-motion crisis quietly unfolding beneath its surface. Let's get into it. Hoover Dam has been one of the most recognizable engineering achievements in American history since it was completed back in 1935. It's a 726-foot-tall concrete arch gravity dam holding back Lake Mead, the largest reservoir in the United States by volume. And for nearly a century, it supplied power and water to millions of people across Nevada, Arizona, and California. But the Colorado River, the river that fills both Lake Mead and its upstream neighbor, Lake Powell, has been shrinking for a quarter century. Since 2000, the entire river basin has been locked in what climate scientists call a megadrought, and 2026 has turned out to be one of the worst years yet. A punishingly weak winter snowpack combined with an extreme summer heat wave has pushed water levels in both lakes towards thresholds that engineers have spent decades trying to avoid. So how bad is it exactly? And why does it matter beyond the two states that border these reservoirs? Let's start with the numbers, because they tell the story clearly. As of early August 2026, Lake Powell sat at roughly 3,522 feet in elevation, holding about 23% of its total capacity. Lake Mead sat at roughly 1,041 feet, holding about 27%. Combined, the entire Colorado River reservoir system was down to around 32% of capacity, compared to 39% just 1 year earlier. That's not a small year-over-year dip. That's a system losing ground fast, even after years of conservation efforts across the basin. Here's where it gets genuinely urgent. Glen Canyon Dam, which forms Lake Powell, has what engineers call a minimum power pool, an elevation of 3,490 feet, below which water simply can't reach the intake penstocks that feed the turbines that generate power. As of this summer, Lake Powell was sitting only a few dozen feet above that line. Reclamation's own projections put Powell at around 3,508 feet by the end of 2026, a narrow margin that's forced federal water managers into genuinely unprecedented emergency measures. In April 2026, the Bureau of Reclamation began what amounts to triage across the entire river system. The agency reduced its planned water release from Lake Powell for the year, from 7.48 million acre-feet down to 6 million, while also arranging for up to 1 million acre-feet of water to be released from Flaming Gorge Reservoir, a separate reservoir upstream on the Green River in Utah, essentially borrowing water from one part of the system to prop up water levels in another. That decision protects Glen Canyon Dam's ability to keep generating power, but it comes at a direct cost to Hoover Dam downstream, because less water released from Powell means less water eventually reaching Lake Mead. So let's talk about what's actually happening at Hoover Dam itself, because the mechanics here are worth understanding properly. Hoover Dam's power output depends heavily on something engineers call hydraulic head, essentially the vertical distance the water falls from the reservoir surface down to the turbines. As Lake Mead's water level drops, that head shrinks, and each of Hoover's turbines generates meaningfully less electricity per unit of water passing through it, even before the lake gets anywhere close to a hard cutoff point. That's why Hoover's output has already fallen by an estimated 40% below its maximum rated capacity this year alone, well before hitting any kind of dramatic shutoff threshold. There's an even steeper cliff coming though. According to Bureau of Reclamation projections, when Lake Mead drops below an elevation of roughly 1,035 feet, Hoover's hydropower generating capacity is expected to fall by around 70% almost immediately. As of this writing, Lake Mead sits only about 15 feet above that threshold, and depending on how the rest of the year plays out, some water managers have suggested that critical line could be crossed as early as this coming winter, or potentially pushed off until sometime next year if conditions improve slightly. Beyond that, there's an even more severe threshold, 895 feet, the elevation of the bottom of Hoover's intake towers. Below that point, gravity simply can't deliver water to the turbines at all, a condition known as dead pool, where the dam effectively stops generating power completely. Current projections don't have Lake Mead approaching that extreme scenario in the near term, but the fact that engineers are now openly modeling and discussing it at all is itself a meaningful signal of how seriously the situation is being treated. Now, here's a detail that genuinely surprised even some of the engineers studying this system. Low reservoir levels don't just reduce power output, they can actually damage the infrastructure itself. As water levels drop, turbines and outlet work start pulling in air alongside water, a phenomenon called cavitation. When tiny air bubbles collapse inside flowing water under pressure, they generate small shock waves capable of eroding concrete and metal over time. Engineers at Glen Canyon Dam have already documented new, previously unseen cavitation damage after using emergency steel bypass tubes at unusually low reservoir levels back in 2023. As one river studies expert put it, this is a situation that's been calculated and modeled for years, but never actually tested in practice, because the system simply has never operated this low before. So what happens if the water keeps dropping, and what can actually be done about it? Federal water managers have proposed several potential engineering fixes at Glen Canyon Dam specifically, since protecting Powell's power generation has become the more immediate operational priority in the system right now. Options on the table include boring entirely new outlet tunnels through the dam structure, relocating and re-engineering the existing river outlet work so they can generate power more efficiently at lower reservoir levels, or even constructing a bypass tunnel around the dam entirely. Any of these approaches would be a massive undertaking, with estimated costs ranging from $500 million up to $3 billion, and construction timelines stretching across multiple years, all while the dam continues operating under increasingly marginal conditions in the meantime. Beyond the engineering fixes at the dam itself, Reclamation has adopted what it's calling an adaptive management framework for Colorado River operations running through 2036, deliberately avoiding a single rigid rule set in favor of a more flexible approach that can respond to changing conditions year to year. It's a tacit acknowledgement that the old operating assumptions built around a river system that no longer exists in its historical form simply don't hold anymore. Let's talk about who actually feels this, because it's not an abstract engineering problem. It has direct consequences for people's electricity bills across the Southwest. Utilities across Nevada, Arizona, and parts of California hold long-term contractual allocations of Hoover Dam's power output, historically some of the cheapest electricity available anywhere in the country, since hydropower has minimal ongoing fuel costs once a dam is built. As Hoover's output shrinks, those utilities still have to deliver the same amount of electricity to their customers, which means sourcing replacement power from other sources, typically at meaningfully higher cost. Grid reliability analysts at the Western Electricity Coordinating Council, the regional body responsible for monitoring grid stability across the western states, have been actively modeling low hydropower scenarios to understand just how significant the broader grid impact could become as this trend continues. It's worth being clear, though, that experts studying this situation aren't describing anything close to widespread blackouts. As one grid specialist put it, this doesn't mean the lights go out. It means other, typically more expensive resources have to compensate for the lost hydropower capacity. Some smaller utilities like Lincoln County in Nevada have already begun diversifying into solar specifically to help cushion the impact of Hoover's declining output, a trend that's likely to accelerate as more utilities across the region reassess just how reliable Hoover's power allocation is going to be over the next decade. So how does the American Southwest actually get out of this? The uncomfortable truth is that no single engineering fix solves the underlying problem, because the underlying problem isn't really an engineering problem at all. It's a climate and water supply problem that's been building for 25 years, driven by a quarter-century of below-average snowpack across the Rocky Mountains, the primary water source for the entire Colorado River system. Engineering interventions like new bypass tunnels or reconfigured outlet works can help the existing infrastructure operate more reliably under lower water conditions, but they can't manufacture water that simply isn't falling as snow in the mountains anymore at the volumes the system was originally designed around. What's clear is that Hoover Dam, one of the most celebrated engineering achievements in American history, a structure that once seemed like a permanent, unshakable pillar of the Southwest power and water supply, is now operating under conditions its original 1930s engineers never planned for. It's not failing outright, and it's not likely to stop generating power entirely anytime soon, but it is running leaner, less reliably, and more expensively than at any point in its 90-year history. And the system feeding it shows no clear sign of returning to the conditions that made Hoover's original design assumptions realistic in the first place. For now, water managers keep moving water between reservoirs to buy time. Engineers keep modeling scenarios nobody expected to actually need, and somewhere in Nevada desert, Lake Mead keeps dropping, foot by foot, toward thresholds that were once considered a purely theoretical worst case. And as always, if you enjoyed this video and want more from the definitive channel covering the world's biggest infrastructure stories, make sure you're subscribed to Apex Infra.